Lifecycle Cost Analysis (LCCA) offers a holistic view of highway infrastructure expenses encompassing initial construction, operation maintenance, and replacement costs. This method aids in making informed decisions by balancing upfront investments with long term value. LCCA ensures sustainable and cost effective choices in highway projects, optimizing financial resources over the project's lifespan. Life cycle cost analysis evaluates a project's total cost from construction to replacement. It identifies the best long term value, not just the cheapest initial option, by considering future expenses. In highway projects, life cycle cost analysis compares alternatives like pavement types and bridge designs to find the lowest total cost over time. Life cycle costs in highway projects encompass initial construction, including design, materials, labor, and equipment. Maintenance involves routine and periodic activities to preserve functionality. Rehabilitation covers major repairs to extend service life. User costs account for travel time, vehicle operation, and delays. End of life costs include demolition, recycling, or disposal expenses. In highway projects, optimizing total cost involves evaluating future maintenance and operational expenses, not just initial bids. This approach improves budgeting by forecasting costs, helping agencies plan maintenance and avoid budget shocks. It encourages sustainability by demonstrating how quality materials reduce long term disruptions and informs decision making through structured comparisons using real data and assumptions. Key steps in life cycle cost analysis (LCCA) include defining objectives and alternatives, such as minimizing total cost or maximizing durability. Develop a cost breakdown structure covering construction, operation, and end of life expenses. Estimate costs and timing using historical data. Apply discounting to compare future costs in present value. Analyze risk and uncertainty in costs and maintenance needs. Agency costs in life cycle cost analysis encompass construction, maintenance, rehabilitation, and administrative expenses. Construction costs, though substantial, often form less than half of total life cycle costs. Maintenance involves routine and periodic activities, while rehabilitation includes major repairs. Administrative costs, covering inspection and planning, are crucial yet frequently underestimated in long term budgeting. User costs in life cycle cost analysis (LCCA) encompass travel time costs, reflecting the economic value of time spent traveling, including delays. Vehicle operating costs cover fuel, tire wear, and maintenance, influenced by pavement conditions. Crash costs account for accidents' economic impact, while delay costs arise from congestion during maintenance, affecting personal and commercial transport. External costs in life cycle. Cost analysis encompass environmental impacts like emissions, noise pollution, and habitat disruption. Modern life cycle cost analysis uses monetization techniques to quantify these. Additionally, community impacts such as property value changes and business disruptions during construction are considered, offering a comprehensive view of infrastructure's societal impact. Discounting in life cycle cost analysis (LCCA) involves converting future costs to present value using the formula present value fast future value. 1 plus R, ln. The discount rate, typically 3 to 7%, affects life cycle cost analysis outcomes by balancing initial and future costs. It reflects opportunity cost, inflation, and risk, influencing decision making in infrastructure investments. Risk and uncertainty analysis in life cycle cost analysis is crucial for accurate predictions. Deterministic analysis uses single point estimates, while sensitivity analysis examines changes in results with varying inputs. Probabilistic analysis, the most advanced method, employs statistical distributions to model potential outcomes, offering a comprehensive view of possible scenarios and aiding decision makers in understanding risks. A 30-year LCCA example compares asphalt and concrete pavements. Asphalt has lower initial costs but higher maintenance, while concrete has higher upfront costs but lower long term expenses. Discounted to present value, concrete's life cycle cost is $2.55 million versus asphalt's $2.9 million, illustrating that higher initial investment can lead to greater long term savings. Flexible pavements like asphalt offer lower initial costs and faster construction, but require frequent maintenance and have a shorter lifespan. Rigid pavements, such as concrete, have higher upfront costs and longer construction times, but excel in durability and performance under heavy loads. Over 20 years, concrete often proves more cost effective due to reduced maintenance needs. The LCCA Excel template is a comprehensive tool for calculating lifecycle costs of infrastructure projects. It includes sections for initial construction, maintenance, rehabilitation, and user costs. The results dashboard visually compares alternatives with present value calculations and cost breakdowns. Sensitivity analysis tools test variable changes, identifying impactful factors on LCCA results. In this exercise, students will compare 20-year life cycle costs for rigid and flexible pavements using an Excel template. They will define project parameters, estimate initial construction costs, and develop maintenance schedules. By calculating present values with discount rates, students will determine the most cost effective pavement type under different scenarios. Life cycle cost analysis optimizes financial decisions by identifying cost effective solutions, saving taxpayer dollars through strategic investments. It enhances planning by forecasting maintenance needs, ensuring accurate budgets and schedules. Life cycle cost analysis also promotes transparency, offering a data driven decision making process that builds stakeholder trust. Additionally, it supports sustainability by favoring durable solutions that minimize environmental impacts. Value engineering (VE) leverages life cycle cost analysis (LCCA) to enhance project value by analyzing functions and costs. Lifecycle cost analysis provides comprehensive cost data, aiding in identifying design alternatives that maintain functionality while reducing lifecycle costs. This ensures value improvements focus on long term performance. Teams generate options, analyze lifecycle costs, evaluate function versus cost, and select the optimal solution. Lifecycle cost analysis requires historical cost data, including past project costs adjusted for location and inflation. Performance models such as deterioration curves help estimate service life for materials. Traffic information, including current volumes and growth projections, is crucial for estimating user costs. Economic factors like discount rates and inflation projections are essential for accurate life cycle cost analysis. LCCA faces challenges such as data uncertainty, especially with new materials lacking historical data. Discount rate sensitivity can alter cost effectiveness conclusions. Non monetary factors like aesthetics and environmental benefits are hard to quantify. Institutional barriers like separate capital and maintenance budgets hinder life cycle thinking, as construction departments may not account for future maintenance costs. In Colorado's Interstate 25 corridor, life cycle cost analysis favored concrete pavement, resulting in 40% lower life cycle costs over 40 years. Florida's coastal bridges use corrosion resistant materials with a 25% higher initial cost, extending service life by 30 years. Washington's stormwater management found permeable pavements more economical, despite 15% higher construction costs by integrating environmental costs. Life cycle cost analysis (LCCA) can lead to 30 to 50% savings by reducing total costs when properly implemented. Notably, 70% of life cycle costs occur post construction. A 20-year analysis period is recommended for highway projects. LCCA justifies higher initial investments for long term savings. Next steps include using Excel templates to compare costs and integrating environmental and social factors.